All right, integrated 3 students, we are starting our new section, geometry, but we're going to be talking about circles today. Okay, we are going to be talking about circles. So let's go ahead and get started. All right, so the first place that we're starting with this unit is we're going to be talking about what is a circle to begin with. Okay, now all of you should have already received the assignment where you're doing your definitions. That's due today is the 9th, and it is due this evening. So those definitions for parts of a circle, make sure that we have those written down. But the most important thing is to understand what a circle is. Okay, so if you haven't written that definition down, go ahead and think about what is a circle as far as its definition. All right, I'm not going to pause the video or anything. We're going to go right into it. But we know how to construct a circle. At least we've done that on Delta Math a few times. In our Delta Math section where we had to do the constructions, we could construct these circles. If I make a compass, so compass is the tool we use, we can drag this and we can draw ourselves a circle, right? So this is essentially what we need for our definition, okay? On my little tool shelf here, I have this compass, and I can click and drag and create a circle. All right, so this idea is that we're just incrementally creating this. And I want to talk about sort of my thoughts I didn't really learn a proper definition for a circle until I got into I'd say my 4th year in college. I always thought about it this way. Here I have an application that we're going to be using together today, so I'll link this in a second. But I always thought of a circle as a regular polygon. So if I click this tool here and I draw a line, I can create a regular polygon. One with 4 sides would be a square, right? Undo that. Let's make another. One with 5 sides, that is a pentagon, right? So it's making those. And I remember, I think it was in middle school or early high school, I can't remember when, but I remember playing with like a tool like this. Here's 6 sides, it's a hexagon. You'll notice that it's starting to create a shape that is circular. Here's an octagon. It looks like a stop sign, right? And I thought, okay, well, what happens if I make a 100-sided figure? Well, if I zoom out, it definitely looks like a circle, right? So for a long time, this was my definition, was, oh, it's a infinite-sided polygon. But that's not actually the case. Let's do one with 1,000 sides. Okay, 1,000 sides. It's going to take the computer a minute to do it, but it will do it, and it's going to probably be pretty slow. But this has 1,000 sides, and you've probably never even considered making a shape like this, but it obviously looks like a circle when you do it. However, when I brought this idea up in my college level course, one of my classmates respectfully told me, hey, that actually doesn't work for a circle. Okay, so if you went into this thinking, oh, a circle, is just a round shape, or maybe like me, it's a figure with infinite sides, because if you look at that, it almost looks straight, right? But that's actually not the proper definition, because as soon as like I put one of these shapes, if I put the point like in here, it sort of blows up the definition of what a circle is. If I add another 2 sides to this, it makes 1,001 sides, okay? And if we got rid of that, oh, you can't see that, hold on. If I did something like this, it still has like an infinite amount of sides, but now it definitely doesn't look like a circle anymore, but it still sort of fits my original definition. So we have to change our definition of what is a circle. So this is how I want you to think about it. If I were to draw this circle here, I'm going to zoom in so we can get a real good image. If I'm going to draw a circle, I can go around and I can just add dots, right? Okay, and if I just kept doing this all the way around, what I'm doing right now, it really is the true definition of a circle, right? Imagine these aren't like lines, right? Because circles technically are not lines. If we look at this one here, this is not a line, okay? Definition of a line is a straight one-dimensional geometric object that goes to infinity in both directions. Now this does not work like that, okay? This is not straight. What we have here is just a collection of infinite points. So like I'm illustrating here, all I'm doing is drawing points on with this compass here, okay? And what ends up happening is I'm drawing an infinite amount of points all the way around this center point. Every single point on this circle is the equal distance from this center point. Every point is the same distance. So the best definition that we can have for a circle, so we're going to write this down. I don't know what you already have in your notes, but this is really all we need, okay? It is a group of points that are equal distance from a central point. This is all we need. Now, a lot of you may have thought, oh, well, what about 360 degrees? What about, it looks round, right? We don't need those. We don't need those definitions for this. That is not something that we need. Even though it is, in fact, round, or it looks to be what we would call round, that could also describe a lot of shapes, like a sphere, which is three-dimensional. A cylinder would be round. Even two-dimensional, you have ovals and ellipses and things like that maybe you hadn't considered. So this is truly the best definition for a circle, okay? So make sure that you have that down to get us started today. That's what we want to start with, okay? Now, we're going to talk about a pretty simple idea to start things off. This is actually one of the standards for this class, but it's going to be just something I'm going to say, hey, check this out. That's kind of all we're going to be doing with this. So we're going to write this down. All circles are similar. Okay? That is the rule. All circles are similar. So let's talk about this statement, this idea of similar, right? That's what we want to do. So last year in iMath 2, you would have answered questions that look like this, right? This is an iMath 2 question, all right? And in this question, it would tell you solve for x. The triangles in each pair are similar. So you would solve this by creating a proportion. You would say, oh, it's 6 compared to 3x equals 5 compared to 10. And you could easily cross multiply and solve that. So are all triangles similar though? No, that's not true. This triangle it tells us it's similar, but that meant this angle here and this angle here were congruent, and you had that angle similarity right there. Maybe you remember that from last year, maybe not. My face-to-face learner said that they kind of do, roughly. But you could solve questions, you could find missing links based on two shapes being similar, okay? So we don't have to do any of these proofs for circles, because no matter what the size of the circle is, here's one here, all right, and I move it over here. I'm going to draw another one down here, but I'm going to make it a lot larger. These circles are similar, okay? And that has to do with the fact that every circle contains 360 degrees within it, okay? So I want to talk about a problem that was solved. And again, this is all just, hey, for your information, this is a fun fact. This idea was discovered, or this idea of similarity was discovered in the BC era. So I'm going to share with you guys one of my favorite math history facts, or just a story from history, okay? And how a Greek mathematician was able to solve for the circumference of the earth. They were able to figure out how far around the earth's circumference was before they even discovered America, obviously, because that didn't happen until many years later, and a long time before anyone was able to get an accurate calculation of how far around the Earth actually was. Okay, the Greek mathematician was Eratosthenes. He was extremely close to getting it right for being such a long time ago. Okay, so we're going to watch a video explaining how he did that. Okay, and hopefully history is something that interests you. If not, just it's only 2-minute video, so maybe just hang on to it, or hang on and watch it and check out how he did it. All right, so here we go. We're going to watch this.
In the mid-20th century, we began launching satellites into space that would help us determine the exact circumference of the Earth, 40,030 kilometers. But over 2,000 years earlier in ancient Greece, a man arrived at nearly that exact same figure by putting a stick in the ground. That man was Eratosthenes, a Greek mathematician and the head of the Library of Alexandria. Eratosthenes had heard that in Syene, a city to the south of Alexandria, no vertical shadows were cast at noon on the summer solstice. The sun was directly overhead. He wondered if this were also true in Alexandria, so on June 21st he planted a stick vertically in the ground and waited to see if a shadow would be cast at noon. It turns out there was one, and it measured about 7 degrees. Now, if the sun's rays are coming in at the same angle at the same time of day, and a stick in Alexandria is casting a shadow while a stick in Syene is not, it must mean that the Earth's surface is curved. And Eratosthenes probably already knew that. The idea of a spherical Earth was floated by Pythagoras around 500 BC and validated by Aristotle a couple centuries later. If the Earth really was a sphere, Eratosthenes could use his observations to estimate the circumference of the entire planet. Since the difference in shadow length is 7 degrees between Alexandria and Syene, that means the two cities are 7 degrees apart on Earth's 360-degree surface. Eratosthenes hired a man to pace the distance between the two cities, and learned they were 5,000 stadia apart, which is about 800 kilometers. He could then use simple proportions to find the Earth's circumference. 7.2 degrees is 1/50th of 360 degrees, so 800 kilometers times 50 equals 40,000 kilometers. And just like that, a man 2,200 years ago found the circumference of the entire planet with just a stick and his brain.
All right, pretty incredible that they're able to do that. So let's talk about how knowing that similar circles is helpful. Okay, so we'll go back to this diagram that they created. So the parallel sun rays, the shadows make all the difference. So Syene was actually on the equator, and at noon at the equator, the sun should be directly down. Okay, on whatever is there. So there shouldn't be any shadows exactly at noon on the equator. Okay, but the Greeks, they had plenty of time back in the day after they had Alexander conquered the world. They had a lot of real estate before the Romans took over. So a lot of them, we owe a lot of geometry and the understandings of that from the Greeks. They discovered all of this stuff with just sticks, sand, and just a lot of free time, really, is what happened. But these parallel rays, so we know from iMath 1, and we've talked about parallel lines a little bit, or we worked with parallel lines on the coordinate plane on our last test, but we didn't really go into the properties of this. But this is opposite interior angles, okay? They knew that was a property as well. So this opposite, from the shadow, it's 7.2 degrees, and if we extend the sun rays infinitely through the Earth, we know that this one should go straight to the center, straight down to the center, and this one's going to have an angle. So opposite interior angle says, okay, that's a 7.2 degree angle created between these two sticks that are in Egypt, okay? And so by knowing that every circle is similar, they're all circles, no matter what the size, even one so large as the Earth, is going to have 360 degrees around, they're able to create a proportion. So, and he hired somebody to walk that distance there to figure out the measurement. It's 800 kilometers. And they set up this proportion. 7.2 degrees is out of 360. So the rest of the Earth would be 360 degrees. And they know for that 7.2 degrees, it's 800 kilometers. That means simple proportion. I can just cross multiply and find the distance of the Earth, 50 times 800, and you get very close to the true kilometer distance around the Earth. Quite incredible with this fact that all circles are similar, okay? So this is just there's not really going to be an assignment that's dealing with this, but this is just something for your interest, and I mean, it's one of our standards. It's important to know that all circles are similar, but we're not going to have really like problems that we'll be working that necessarily deal with that, okay? All right, I'm going to start a new page. We're going to start looking at some other ideas here. We're going to start, this is not something that we defined, but we're going to talk about, we'll put a little star here. We're going to say central and inscribed angles. So write this in your notes, central and inscribed angles, okay? And we are going to, before we write anything else down, I'm going to pause the video and I'm going to send you a link to this website here, okay? So I'm going to clear all this, don't save, okay. So I'm going to be pausing the video to send you a link. All right, so hopefully you have this opened up either on another tab or you can split your window, however you want to do it. But definitely take your time with me on this. You're going to be creating diagrams as I'm instructing you on what to do. I'm going to pause it throughout this, and as I ask questions for you guys to think about these. But over on the left side, let me actually refresh my page here because you don't have all the tools showing, and I don't want to show all those just yet. So you should see just these basic tools over here. And the first thing we want to do is we want to create a circle. So I want you to click this circle with center. I'm going to try to go pretty slow on this. Circle with center, you click it and it gives you directions. It says select center point, then point on a circle. So really all we need to do is click and drag with our touchpad or our mouse. So we're going to click and drag, and it's going to create a circle whatever size you want right away. So I'm just going to click and release probably about here. Okay, so it creates the points. We have A and we have B. And so we have created a circle on GeoGebra. All right, this is an infinite amount of points equally distanced from A. And we've highlighted one point B, okay? So if you need to pause and rewind, go ahead and do that. I'm not gonna pause it here, but if you need to go back and try to figure this out again, just go back and watch it. Take your time with it. The next thing I want to do is I would like you to click the point tool here, and this is going to let us add an extra point somewhere on our circle. So you're going to click that, and then you're going to add a point. Let's just put one here, okay? And that's point C, okay? So we have another point on the line. Now what we want to do is we want to grab the segment tool, and we want to create the segments by clicking one point at a time. I want to create AB, and you click again, AC. All right, cool. So we've created these segments. Now, here's the question. I will pause it for this. What are these parts of a circle called? If you've done your definitions, you have it written there, and also this should be something you learned a long time ago. What are these? What is AB and AC? That's the question. All right, so you should have answered radius, okay? Now, what do we know about radius or radii? Well, all of them should be equal in this circle, okay? So let's actually show that. So click the More tool on the left, and you're going to scroll down, and you're going to find this measure. That's what we want. See the one that says measure? And we're going to click this distance or length. So that's what's really nice about this software, is that we have so many tools available to like prove that things are congruent or to show measurements and really confirm things. So you're going to click that, and it tells you what to do. You select 2 points, a segment, a polygon, or a circle. So we're just going to click 2 points, or excuse me, a segment. Click AB, and then go ahead and click AC. And look at that. They should be congruent to each other, like we said, since they're both radii. Okay, they're both the radius of the circle. So whenever you're like scrolling down, you'll see this little blue arrow. It's a move or drag. You also have it up here. Everybody go ahead and click that. And now you're able to actually manipulate this diagram. If I grab B, I can make the circle smaller or larger. It's pretty nice. And you'll notice how these the radius are going to change but they're always congruent. Now you can grab C and rotate it around, drawing a radius in a different direction. You'll notice it's always going to stay the same. So we start to really get the sense of what this is going to be able to do for us. We're going to be able to create some really interesting diagrams on here. And for me, this is so much fun to me, being able to do this. This is when I really like, I always feel like a math artist when I'm working on some of these things, but we're going to see some really very cool, interesting ideas and concepts within within these circles. It's going to be great. Okay, so let's go ahead and do something else. Okay, we need to write down our definitions that we started. So now that we've got that started, let's go ahead and write this: central and inscribed angles, and we're going to start with central angle definition, and then we're going to do inscribed angle definition. We're going to talk about the difference between both. Okay, so I'm going to get a definition pulled up for us. All right, so first definition is of a central angle, an angle at the center of the circle with endpoints on the circle's circumference. So I'm going to pause and let you write that. Okay, so we've got that written. Next definition is inscribed angle, an angle made from the point sitting on the circle's circumference. So I'm going to pause and let you write that. Okay, so you've written both definitions, so now I'm going to ask a question. I know there's a lot of pauses in this. It's very interactive today. We have an angle that we've created here, so you have a multiple choice question coming at you right now. Is this a central angle or is it an inscribed angle, based on the definition we just wrote down? So I'll give you a second to answer that. All right, so this is a central angle. Why is it a central angle? Well, the angle at the center of the circle with endpoints on the circle's circumference. Essentially, the vertex of the angle is the center of the problem. Okay, everybody needs to make sure they go back to this. Be ready to go back and work on this GeoGebra. We're going to add something else. We have a central angle on here. Or you have created a central angle, but now we want to create an inscribed angle. Okay, let's build an inscribed angle on this. So what you need to do is we need to go back up to the top here, and we need to add a fourth point, okay, or really a third point on the circumference. So I want you to grab the point tool, okay, grab that point tool, and we are going to add a point on the opposite side of A here. So we're going to put it probably here, okay? Let's start it there, and let's connect D to B and D to C. And now you really get to see the dynamic ability of these diagrams. Move D around, and you see that these two angles are on the same. We'll call this the arc CB here, but we have an inscribed angle that we've created because all the points. Here's our definition: angle made from points sitting on the circle's circumference. So we're going to call the outside of the circle, or that edge of points, the circumference, and this is sitting on there. And then we have our central angle. Okay, so we have created both. All right, now we're going to do some more measuring. So I want you all to do this with me. Hopefully you've got this. If you need to rewind, do that. But now I want you to do this. Scroll down to the measure section here, and we want to measure the angles of both of these angles. All right, we want to see what their measurements are. So we're going to click the angle tool, and look what it says at the bottom. It says select 3 points or 2 lines. So we have 2 lines that we can pick. Let's go ahead and click AC and AB, so we get an angle. Go ahead and click angle again, and you click DC and DB. All right, now let's click the move tool. You can move some of these parts around, like I can move the angle up, and you can clean this up a little bit so you can see the angles. What I'd like you to do is move all of these parts around. It doesn't matter, B, C, whatever, okay? Whatever you want to do. And I want you to take a moment. I'm going to pause it, and I want you to write down something that you notice about these angles, okay? there is something happening with these angles, and hopefully you see it. So I'm going to give you a few moments to play around with this. I'm going to pause it, and you're going to write up what you see happening with these angles. Now, if you're just completely lost, and also if you need to pause and rewind to see how I did this, do that. But if you're just lost and not understanding what is actually happening in the diagram, then you can say, I don't know. I'll be like, okay, that's fine. But hopefully you're able to see what's actually happening here, okay? All right, so hopefully you guys noticed that when you make this angle, or when you're moving these pieces around, if I move C around and I make it, let's make it 80 degrees. Okay, what do you notice about the central angle? Well, look at that, or excuse me, the inscribed angle. It is half of that angle, right? Now that's sort of an exception when it goes up here. We won't really talk about the rule for this, but when it's over here, it's going to be half. Okay, it's going to be half of the angle, and that's always going to be true. So we're going to write down a rule for this. So let's put this down in our notes. Inscribed angles are always half the degree measure of a central angle that intersects the same arc. So that's going to be one of our big theorems, really, is what this is that we've discovered. Now, we were able to see that, and hopefully that all makes sense to you. We're able to see that in a few minutes, whereas imagine if you're in ancient times and you had, sand and a stick with string to draw all of this. You had to confirm this a long time ago, and it probably took longer than a few minutes to actually see this property take place. But that is the power of this software. One of my favorite things to imagine, I know this is nerdy as all get out, but imagine one of the ancient Greeks coming back and using this software and just the things that they could probably figure out with their time. So it's I know that's nerdy, but it's something that always gets me excited, is to see or to imagine this got discovered in BC time, right? And it must have taken them forever, to confirm the angles and do the measurements and all that. Must have taken them a very long time. Anyway, enough nerding out. Let's actually apply this information to some questions. So let's go ahead and get Delta Math opened up. So go open up Delta Math on your 5.2 circles. You'll see that section is newly opened up. I actually need to move some parts around here. Yeah, that's fine. Complete edit. I'm definitely going to be adding more to this as we go on, but you should see it'll look like this. The first thing we're going to talk about, what we just wrote down is called the inscribed angle theorem. Okay, so you only have 6 questions. And this is what they look like, okay? So we have the circle D with the measure of angle CFE. So CFE is 39 degrees. All right, so I'm going to draw on this. So we know that this is 39 degrees right there. So we want to find the measure of CDE. So CDE, well, really what we need to know is which one is the central angle and which one is the inscribed, okay? Remember, inscribed is on, all points are on the circumference. So that would be CFE is inscribed and CDE is central. And we said inscribed angles are always half the measure of a central angle that intersects the same arc. So you'll notice that these are intersecting the arc CE, and this angle will be half of this one. So really all we need to do is we need to do 39 times 2. That gets us 78. So on Delta Math, we're just going to type in 78, and we're done. So yes, these problems are going to be pretty straightforward as far as what you need to do. Sometimes you have to do central to inscribed. Sometimes you have to do inscribed to central. Let me find one that looks pretty difficult. I know that some of you will have questions. Okay, so this one looks kind of weird, right? But as long as you're able to identify which one is central and which one is inscribed, you should be okay. So PSR, they give us that one, PSR, that is the inscribed angle here, because all of those points are on the circumference. Then we need to find PQR. So PQR, well, it's double. So that's going to be 68. Okay? So we're going to put 68 in here. We got it. And there's just a ton of different examples that you can see. Oh, this is a good one here. Okay, this is a good one. Let's see about this one. This is an interesting one. Let me think about this one. All right, so looking at this one, BED, really it all depends on where the points lie. So BED is the inscribed angle, and we know that that's 66. And we're trying to find BCD, which is this angle here. So it looks like they are the same line. I mean, it is the same line here. So it's going to be double that angle. So we're going to get double that, which is that's going to be 132 right here, 132. So that should be correct. But you are going to see a lot of different looking angles on here, different ways that those are presented. Some of them will look too complicated, but as long as you identify which one is on the axis and which one, or on the circumference, and which one isn't, you should be in good shape. Okay, so you're always looking, read the angle, follow along on the diagram, and try to find that. Okay, we have something else that we want to look at. I want to show you all this, and we're going to write down another rule. Watch what happens if I make CB right here 180 degrees, if I can get it perfect here. Now, and you can try this on your diagram as well. You don't have to though, because I'm going to eventually get it. There it is. Okay, so 180 degrees is what I have here in my circle. Okay, and I want you to notice, obviously the rule still follows that it's going to be half, but what kind of angle is this here that we're seeing? No matter which way it goes, it's always a 90-degree angle. Okay, also CB being 180 degrees means it's essentially a straight line, and it's going straight through the center, so we have a name for that. That's called the diameter, right? So if your central angle is the diameter, then the inscribed angle will always be a right angle, 90 degrees. So this is a very important rule. So we're going to write this down. I'll go back to our slide here. Okay, if the central angle is 180 degrees, and we'll say the diameter, then the the inscribed angle will always be a right angle. We'll say in parentheses 90 degrees, which follows the rule of half the measure. It still works there. Okay, so we're seeing that. This is almost like a sub point of the first one. Okay, so I'll have you make sure you wrote that down. All right, so we've got that down. Let's move on to the next topic. Definitely I'm going to be adding more to this delta math, but for now we're starting with these three sections here. I'm probably going to add these last three down here. I'm probably going to bump those down a little bit. We're not ready for those, and add a few more like custom problems with in between here. Okay, so we're going to talk about arc measures. Okay, we're going to look at these questions right here. Okay, so in your notes we'll start a new section. Again, all of this is there's simple rules that we're going to be writing down, but there's a lot of them. So that's what makes geometry. That's what can make geometry tough, is that there's a lot of rules. So we're going to talk about this arc measure. This is sort of the title of this section. Arc measures. Okay, so let's make another section with a note. The measure of an arc is congruent to its intersected. The measure of an arc is congruent to its intersected central angle. So this is our rule for this. All right, this is our rule for this, and that helps us answer this. So it says we have this. It says in a circle D, and you can pull up your delta math as well. In a circle D with m greater than, or excuse me, the measure of angle, not greater than, I don't know what I'm talking about. The measure of angle CDE, so CDE is 126. Find the angle measure of the minor arc CE. So CE goes from C, and we're following it along on the circle. Okay? Following along on the circle. Now with the rule we just wrote down, the measure of an arc, okay, is congruent to its intersected central angle. So for this one, the answer is 126. That's how we do that, okay? Now it becomes a little more difficult when we get to questions that look like, let me do this one here, okay? Not too difficult, but a little bit more difficult, all right? Because the answer here is not 30. You will get it wrong because it says EHG is 30 degrees. Find the measure of EG. So we want to go from E to G. Now if we put 30, the problem is that 30 is this angle. This is not a central angle. This is an inscribed angle, okay? But if I draw the lines, whoops, let me change that. Black. If I draw a line to the point here, we create the central angle. And what do we know about the relationship between the inscribed and the central angle? Well, the inscribed angle is half of the central angle, so this is 60. Okay, so we almost create this rule that it's going to be double the inscribed angles. Okay, so that's sort of a new idea, or another idea that we can put down. Let's go back to this. Let's edit this, or add another, and we'll say it will be double an inscribed angle. Ooh, this is a long lesson here. I might have to stop after this one. That'll be fine. But so we're doubling this here, this 30 degrees. We're going to double that, so that's 60. Okay. So with that knowledge, it kind of makes this easier. Here, RUT is inscribed, so we double it. It's 50 because of that idea that the central angle would be double. Okay. All right, 37 minutes. I think that's long enough. Let's go ahead and stop it here. If you have any questions, reach out to me, but you should be able to answer these questions, these first two at least. You can check out intersection of chords. That'll be the next lesson we get to. I'll probably put that up tomorrow.